Okay, so in the code, I'm going to do, and in the assignment, you'll do these two things, which is really common in nuclear particle physics when you're designing an experiment for nuclear particle physics, where you simulate some data and then you analyze that data to see how well you can measure the quantity that you're interested in measuring. So I want to simulate the pions decay to a muon, and then we'll build a time spectrum that corresponds to the measurement of the pion decay into a muon. And then we're going to fit that exponential decay curve, that decay curve, to extract the pion lifetime. So I've got basically one cell here that is going to generate the decay curve, or the exponential decay curve that we would obtain in the experiment. So this is the Monte Carlo piece. So previously we had simulated this decay process of a pion decaying into a muon, and we sort of computed the number of pions as a function of time and the number of muons as a function of time, starting with a sample that was all pions and was no muons. So we're going to do the same sort of thing, but this time what we're also going to record is not just the number of pions as a function of time, number of muons as a function of time, but I want to record the number of decays as a function of time, because it's the decays that our detectors will observe. It's the decays that our detectors will register. And so it's the decay curve will build. So that's one little difference. Okay. So some parameters. Firstly, an important parameter is the, if we're going to simulate the lifetime, we've got to have the lifetime. So it's 26 nanoseconds roughly. We're going to build a time spectrum. So I've got a couple of parameters to describe the time spec distribution that I'm going to build. I'm going to build a histogram of the decays with time bins that are 1/4 of a nanosecond, and there's going to be 400 of those time bins. So there's going to be 100 nanoseconds. So that's roughly 4 lifetimes. So we essentially see that the pions completely disappear over those 4 lifetimes. When I do the calculation, I'll keep using a number, a probability for any particular pion decaying in one of those time intervals. And so that probability is just the time interval, so 1/4 of a nanosecond divided by the pion lifetime. At least that's the probability in kind of the limit that time interval is short compared to the lifetime. Okay, so then, you know, I'm going to imagine simulating a particular experiment. So in any particular experiment, I would have some number of pions that I would measure. And so I'm going to pick the number of pions, and I'm going to start with no muons. So set those initial conditions. After I've simulated the data, I want to fit the data to an exponential. And so I'm defining a function here that I can call with curve fit to fit the data. So I'm just defining this function decay, I named it, which is, it just has 2 parameters that correspond to the 2 parameters in a simple decay curve. One is the amplitude at time 0, and then one is the decay constant, or the lifetime. I've also introduced a couple of quantities here, n min and n max. I use these because you might want to play around with what region of the time spectrum that you fit. So we could pick n max and n min to be the region of the time spectrum. Maybe you want to try and fit the whole time spectrum, or maybe you want to look at some fraction of the time spectrum for diagnostics reasons. So I just define those. Okay, so 4 arrays here. One is just the array of the discrete times from 400 discrete times from 0 to 100 nanoseconds. And then I've got arrays corresponding to the population of pions at any particular time. So that's going to walk its way downwards. Population of muons at any particular time is going to walk its way upwards. And then I've got the number of decays. So that will be the, in each time interval, that's going to be the change in the number of pions and the change in the number of muons, because the pions will go down by that number of decays, the muons will go up by it. Then I've got a pair of for loops. Oops, didn't mean to do that, but anyway. I've got a pair of for loops that actually generate the various time distributions. So that's here. One loop is just going to walk me through the time intervals from the initial time 0 up to 100 nanoseconds in these 400 steps. And then the second loop is walking through all the pions that are in my sample, or the pions that are remaining in my sample, and just asking of each pion, does it decay in that little time interval, or does it not decay? So if you look in here, this is where I call the NumPy random number generator for a random number between 0 and 1. If that random number is smaller than that probability, the chance of a pion decaying in that time interval, then that will correspond to that pion decaying. And so I'll register that. I'll increment this counter for the number of decays. And then once I've finished looping over all the pions in my sample, I'll just decrement the number of pions by how many decayed and increment the number of muons by how many decayed. So that's just the procedure. For each time interval, I'm then going to store how many pions I've got in my population, how many muons I've got in my population, and how many decays occurred in that time interval. So these are just me storing these 3 quantities: number of pions, number of muons, number of decays. Okay, so in that executing that cell, then I've simulated my experiment in that cell. And now I can just check it makes sense by checking some plots, right? Making some plots of the number of pions as a function of time, number of muons as a function of time, and the number of decays as a function of time. So that's just this cell here. I'll just look at the plots. Top one is the populations and the lower one is the decays. So in magenta is the pions, number of pions decaying away. In green is the number of muons that are growing. And then downstairs here, this is the number of pions in each time. Sorry, this is number of decays in each time interval. So this is actually what we would observe in a real experiment with our real detectors. We would measure this decay curve here. So those make sense. Look, I'm plotting 0 to 100 nanoseconds. This top plot and this lower plot, I made log plots. So the pion lifetime is just a straight line. The decays here are just the straight line. And you see by a large factor, the pions have basically disappeared over 100 nanoseconds. The decays are vanishing on this time scale of 100 nanoseconds. Okay, so in this cell and in the next cells, I'm just going to start fitting that decay curve to extract the lifetime. I'm going to extract the lifetime to see how well I measure the lifetime. I'm going to extract the chi-squared for the fit to see the quality of the fit. And I'm going to do this several times. So I'm going to do it with increasing sophistication about how I deal with the uncertainties on the data points. And so in nuclear particle experiments where you're calculating, where you're recording events, like you're recording decays, you have counting statistics. So that there's a sort of statistics associated with the fluctuations in the number of counts in any time interval that you see, or the number of decays in any time interval that you see. And so that causes uncertainties on the data points. And that causes uncertainty on the data points that change with time. And so to extract the lifetime, you have to deal with the uncertainties on the data points that are changing with time. And we actually, to extract the lifetime with high accuracy, you'd have to deal with the uncertainties on the data points carefully. And so we're going to kind of look at that counting statistics issue. So just as a starting point, I'm going to fit the decay curve with an exponential decay, but I'm going to just imagine that the uncertainties on each data point are the same. So that's not the case. You know, early times you got thousands of counts. At later times you might maybe got tens of counts in our particular histogram, and that will cause the uncertainties and the fractional uncertainties to change a lot with time. But just as a sort of benchmark, I'll just assume they all have the same uncertainties. So here I am calling, just to remind you, curve fit. So I'm passing it several arguments here. Here's the name of the exponential decay curve function that we're going to fit to the data by adjusting the parameters of the function to minimize the chi-squared. Here are the independent, dependent variables. So the time, our independent variable, and the number of decays, this was our dependent variable. And here's just where I sliced the times and sliced the decays so that I could fit, if I wanted to, I'm not really doing it here, but if just a region of the time spectrum. So just building in that kind of flexibility to use n-min and n-max. This argument here, P stands for parameter, P0 stands for the initial values of the parameters. So it's the initial guesses of the parameters. I wasn't given initial guesses when we're doing the straight line and the quadratic. Often with simple functions, you don't need to give the guesses. It'll just start from somewhere and find the minimum. But with more complicated fits, you really may have to be careful about initial guesses. Anyway, here I gave some sort of initial guesses. I gave a number for the lifetime here that was roughly the lifetime, but you know, I'm pretending I don't know it, so it's not exactly the lifetime. And some number that, you know, I gave it the number of pions, some other number I might know, but it's actually the number of decays it's got to find, so it's not the right life number anyway. Anyway, so I gave it those guesses. It returns the best fit values of the two parameters and the uncertainties on them in this covariance matrix. I wanted to also calculate the chi-squared for the fit to see the quality of the fit. So I calculated the best fit function here. by calling the function with the best fit values of the parameters. I then calculated the residuals, which is the difference between the fit and the data. I calculated the sum of the squares of the residuals, and then I divided by the number of degrees of freedom, which is the number of data points less the number of parameters, to get the chi-square per degree of freedom. So that was all that business. And then I'm just going to print out the time constant, sorry, the lifetime, and I'm going to print out the chi-square and make plots of the fit to the data and the residuals. So this is the result. So maybe just start with the plots. In red is the data points I simulated, and in blue, you can just make it out, I think. That's the best fit curve to the data, exponential decay curve to the data. You can see the quality of the fit a little more clearly down here. So this is the, in green is the residuals. So it's the difference between the fit function and the data. So here you see the residuals, and you see that they're scattered around 0. The lifetime that I extracted was this 26 nanoseconds plus or minus 0.01 nanosecond. However, we should be careful about this because the chi-squared per degree of freedom, because I didn't give it the correct statistical uncertainties in the fit, because I just said that they're all the same, it doesn't really, the chi-squared is, or the chi-squared per degree of freedom is really just calculating sort of the average fluctuation of the data points. And so I wanted to show you this as a benchmark with assuming that the uncertainties are the same, but we really need to be more sophisticated to try and extract the lifetime. So that's just a reference. Okay, so this next cell, I'm going to just, in the next couple of cells after this, I'm just going to fit again and again with more and more sophisticated estimates of the uncertainties so that you get an idea how this is done. So what would be much more realistic for fitting the uncertainties, for specifying the uncertainties on the data points, is to use counting statistics. And if you have reasonably large numbers of counts in a bin, then the counting statistics are binomial statistics or Gaussian statistics, where the uncertainty on a number of counts n in a time bin would be equal to the square root of the number of counts in that time bin. So that if you had 100 counts in a time bin, then the uncertainty would be 10 counts. If you had 10,000 counts in a time bin, then the uncertainty would be 100 counts. And so that would be a simple way of estimating the uncertainties in the time bins. And so we're going to do that. It's not quite right, though. It's not quite right for a couple of reasons. One reason is that counting statistics of the uncertainty being the square root of the number of counts breaks down if you've got small numbers of counts in your time bin, because then the binomial statistics breaks down into Poisson statistics. You can see that it must break down at small numbers of counts by just thinking of the example of you had 0 counts in a bin. If you have 0 counts in a bin, the square root of 0 is 0. And so it would say that the uncertainty on that data point is nothing, is 0. And so that the fit must drive the function through that data point. And that's not right. The other thing that is that we'll see that is not correct in our thinking is that our number of counts that we measure in each time bin are just, one particular measurement of the number of time counts in a particular time bit. The uncertainty that you should use is really the square root of the average number of counts if you have made the measurement many times, not the number of counts if you've just made the measurement one time. And so we'll see that. Anyway, so now I've defined, before I do the fit, I define an additional array of the uncertainties on the number of decays that's equal to the square root of the number of uncertainties. There's one little subtlety that I put in here. I've added 1 to that. And the reason I added 1 to that is that if you have 0 counts in a bin, then you'd be taking the square root of 0. You'd say there's no uncertainty on that data point. And that, it can wreck the fit. It can also wreck calculations of things like residuals because you want to divide by the uncertainty to calculate residuals. And so by adding 1, I'm just trying to, in some really coarse way, fix up a divide by 0 problem or a fitting problem of having uncertainties on data points that are 0. So I'm just making every uncertainty bigger by 1. Okay, so then here, here's my quarter curve fit. It looks exactly the same as the previous quarter curve fit, except I've added 1 extra argument here, which is to specify the uncertainties on the data points. I calculate from the results of the curve fit, the best fit, the residuals, the chi-squared, and then finally the chi-squared per degree of freedom. So I do all those calculations to get the chi-squared per degree of freedom again. The one subtlety, one thing I did difference here, if you look at this line, now I've got uncertainties for the data points based on that calculation of the uncertainties of data points. When I calculate the chi-squared is normally the difference between the data and the fit function squared over the uncertainties on the data points squared. And so in this line now, where I calculate the chi-squared, I'm dividing by the square of the uncertainties, because I know now that the, or at least I've estimated now, the uncertainties. Okay, so here's my results. The plots look pretty much the same as the last pair of plots. So, here's the data points in red, the fit function in blue, and the residuals in green. So things look kind of similar there, look very similar there, I would say. But if we look at the actual lifetime we've extracted and the chi-squared per degree of freedom that we've extracted, the lifetime is now within the error of the truth value that we put in. And before, the lifetime was many, many, many standard deviations from the truth value because we never gave the fit the proper uncertainties on the data point. So now this seems more sensible. And also now the chi-squared seems more sensible. It should be about 1. It should be about 1 within, in this case, 1 over the square root of the number of degrees of freedom. The number of degrees of freedom is like 400. So 1 over the square root of that would be, that's 1 over 20. So we should be within sort of 5% or so of 1. We're further away from 1 than 5%. And that's again because we're still only approximating the errors. We're approximating them as the square root of the measurement, and we're also adding 1 to it. And if you add 1 to all your errors, you're going to underestimate the chi-square, because you're saying that the errors are bigger, which, since you calculate the chi-square by dividing by the square of the errors, you're going to get a smaller chi-square. Okay, but we're getting something that's more sensible now. This cell here. So there's something that you can do better than using the square root of the number of counts in each bin for the uncertainties. Once we've done this initial fit, we've got an estimate of the theoretical distribution that underlies those data points. So instead of using the number of counts in each bin, you can use the fit value as the mean number of counts in that bin if you had made that measurement many times. So imagine, instead of just simulating once or measuring once, we simulated 1,000 times, or we measured 1,000 times. And then we took the average number of counts in the bin. That would be a better estimate for the square root of that would be a better estimate for the uncertainties than the square root of any one of those measurements. Well, we're not simulating 1,000 times and measuring them 1,000 times, but we have fit the data, which gives a better estimate of the mean number of counts than the single simulation, which has the statistical fluctuations. So I'm going to replace my estimate of the uncertainties on the data points with the square root of the values of the fit function rather than the data themselves. I'm just going to make this replacement here. If I compare it with upstairs here, we have this here. So a simple change in the cell here. I also don't need to add the 1 anymore. The adding of the 1 to the uncertainty calculated from the data points was just a cheap trick to get around the problem that if I had 0 counts in a bin, I was going to end up dividing by a 0 or fitting with 0 uncertainty on the data point. But if I use the true fit function, it is never 0 over this time range. There's always some small probability of seeing a decay. And so don't need to fix things up with that kind of cheap trick. I can just use the square root of the fit function. Okay, so now I've redone the fit with these new error bars, and then I've, in the same way, calculated the chi-square per degree of freedom. I get the new fit function, so it might be a little different from the old fit function because I've changed the error bars. It means that the lifetime might be a little different from the prior lifetime because I've changed the error bars. And then the chi-squared will be a little different because I've changed the error bars, which changes the fit, which changes the residuals, and changes the chi-squared per degree of freedom. So I recalculate all those things, and then we can go down here. So now we can look at the data in red, the fit in blue, that it looks pretty much the same as before. The distribution of residuals about 0. It actually looks pretty much the same as before. But if we look at the numerical values, so now lifetime is more centered on the truth. I mean, it's only accidental that it's exactly the truth, but it's centered on the truth. At chi-squared, which was significantly different from 1, it's much less different from 1 this time. And so it's at a level that this can just be maybe a fluctuation. So we've fixed up the chi-squared, and we've got presumably a more accurate determinant of the lifetime because we've used a better estimate for the uncertainties on the data points. Typically what you would do in fits to data or fits to simulations, is you would actually then repeat this procedure. You see, when we fit with the error bars divided by this, determined by the square root of the number of counts, we got a fit function. And then we refit the data with using that fit function for the error bars to get a new fit function. But we're still not completely consistent. Maybe we should take that new fit function, recalculate the error bars, and then do the fit again. And you could imagine doing that again and again and again to prove that everything's stable. And so that's typically what is done to iterate using the fit function for the error bars until you get stable results. So in this last cell, I'm just repeating the same procedure, but it's just with this slightly modified fit function. And so if I run that again, in this case, we see it is pretty much stable. We got the same pion lifetime. We got essentially the same chi-squared. And so we might deem at this point, we've sort of reliably extracted our lifetime.